Welcome to our talk on PyMAF, 3D human pose and shape regression with pyramidal mesh alignment feedback loop. Given a single person image, our goal is to reconstruct a natural and well-aligned body model, including its shape and pose parameters. For the widely used parametric model Simple, the pose parameters are represented as the relative rotations with respect to their parent joints. It means that minor rotation errors accumulating along the kinematic chain can result in noticeable misalignment between the estimated mesh and the input image. Prior work has established two paradigms for 3D human pose and shape recovery, the optimization-based paradigm and the regression-based paradigm. They both have pros and cons in terms of mesh image alignment, physical plausibility, and runtime efficiency. Our work aims to improve the mesh image alignment in a regression-based manner. Let's start with the classic regression-based approach HMR. Firstly, HMR extracts global features using an image encoder, and then predicts the model parameters via an iterative error feedback module. There has also been steady progress going beyond HMR to improve the reconstruction results, such as non-parametric output, proxy representation, and par-based regression strategy. However, some of these solutions need further process, block end-to-end learning, and are costly in computation. By revisiting the architecture of HMR, we find out two main limitations in this classic pipeline. The first one is the lack of spatial information encoded in the global feature. The second comes from the iterative error feedback module, which is hard for the network to perceive the mesh image alignment. To address these issues, we propose PyMAF, a method to reconstruct better aligned body model from a single image. The central idea of PyMAF is to correct parametric deviations explicitly based on the alignment status. Mesh-aligned evidence will be extracted from spatial features according to the reprojection of the estimated mesh, and then will be fed back to regressors for parameter updates. As illustrated in the figures, compared to the commonly used iterative error feedback, the mesh-aligned feedback can take advantage of more fine-grained and position-sensitive evidence for parameter correction. Meanwhile, to leverage multi-scale context, mesh-aligned evidence extracted from a feature pyramid, so that at the beginning, coarse-aligned meshes can be corrected with large steps based on the lower resolution feature. Moreover, to enhance the reliability of the spatial cues, an auxiliary task is imposed on the highest resolution feature to infer the pixel-wise dense correspondence map. The dense correspondence encodes the mapping relationship between foreground pixels in 2D image and mesh vertices in 3D space. In this way, the auxiliary supervision provides guidance for the image encoder to preserve the most related information. In the following, we present the detailed workflow of the proposed PyMAF algorithm. From the beginning, PyMAF extracts a feature pyramid to encode multi-scale spatial information via an encoder. In practice, we use ResNet50 with 3 deconvolutional layers. To obtain the initial prediction, we uniformly sample features from the lowest resolution feature maps with a grid pattern. These grid features are concatenated and fed into a regressor to predict the initial mesh. Based on the current estimated body model, we downsample the mesh and then project it on the 2D plane to extract mesh-aligned features from a higher resolution feature map. Such mesh-aligned features can reflect the mesh image alignment status of the current estimation, which is more informative for parameter rectification. These mesh-aligned features will go through a multi-layer perceptron for dimension reduction and be further concatenated together for parameter update. We can further go through the above steps based on the latest mesh estimation and leverage higher resolution feature maps. Moreover, we impose an auxiliary pixel-wise supervision on the spatial feature map. Specifically, during training, The spatial feature maps at the finest level will go through a convolutional layer to generate the dense correspondence maps. Note that the auxiliary prediction is only required during training. Now let's take a look at the experimental results. We evaluate PyMAF on the 3D human pose and shape estimation task. We can see from the table that PyMAF achieved consistent improvement on 3D PW and human 3.6 million datasets. Here, we would like to point out that the commonly used metric PAMPJPE cannot fully reveal the mesh image alignment performance, as it denotes the MPJPE after rigid alignment of the prediction with ground truth. As depicted in the example, a reconstruction result with a lower PAMPJPE value may have worse alignment performance between the reprojected mesh and image. To qualitatively measure the mesh image alignment of the predictions, we conduct an evaluation on the 2D segmentation and K-point localization. The predicted meshes are projected on the image plane to obtain 2D part segmentation and K-points. Here shows the results of foreground, background, and 6-part segmentation evaluation results on LSP dataset. The optimization-based approach Simplify remains very competitive in terms of 2D alignment metrics and tend to outperform most of the regression-based ones. Since optimization-based approaches are designed to optimize the mesh image alignment explicitly. Though PyMAF is regression-based, it surpasses all other methods, including the optimization-based ones. We also evaluate 2D human pose estimation performance on the COCO validation set to verify the effectiveness of approach in real-world scenarios. During the evaluation, we project 3D K-points from the estimated mesh on the image plane and compute the average precision based on the K-point similarity with the ground truth 2D K-points. We can see that the COCO dataset is very challenging for approaches to human mesh reconstruction, as they typically have much worse performance in terms of 2D K-points localizations. Among approaches recovering 3D human mesh, PyMAF outperforms previous regression-based methods by remarkable margins. We also perform Ablation Studies under various settings on human 3.6 million dataset to validate the efficacy of the key components in PyMAF. We alternatively replaced mesh-aligned features with the global features or the grid features for parameter updates. We've also tried using alternative pixel-wise supervision, such as part segmentation rather than dense correspondence in our framework. Here we can see from the tables that these alternative designs are inferior to our solutions. We also visualize the spatial features of the encoder trained with or without auxiliary supervision. We can see that the spatial features are neater and more robust to the input variations when the auxiliary supervision is applied. Now let's look at some visualization results. We visualize the estimated meshes of PyMAF in each iteration. Though the mean pose mesh is far away from the ground truth, PyMAF can correct the body part drift progressively and get a better aligned human model. Here shows more reconstruction results across different iterations on the COCO and 3D PW datasets. To evaluate the performances of PyMAF on human images with occlusions, we run PyMAF on the 3DOH50K dataset. Note that we only perform testing on this dataset and do not use their data for training. We can see that PyMAF can handle occlusions and produce reasonable reconstruction results. We also visualize some erroneous results. PyMAF fails to handle extreme shapes due to the lack of training data, or the initial reconstruction have severe deviations due to the heavy occlusions and ambiguous link connections in complex scenes. Finally, we present some video results of PyMAF. Note that our method generates the reconstruction results frame by frame and does not use temporal information. Here we show the qualitative comparison with spin and web from the 3D PW dataset. Though PyMAF is a frame-based method, it produces better aligned and more smooth reconstruction results than the temporal-based methods like web. PyMAF can generalize well to the in-the-well scenarios and produce plausible reconstruction results. For the code and more information, please check out our project page. Thank you for watching.